Hey folks, this is Lab 9. In Lab 9 we're going to focus on event-driven interactive programs. A good example of an event-driven interactive program is a game, because you are interacting with it and you're clicking the mouse, pressing the keyboard, and things have to happen on the screen in response to your actions. So we want it to be responsive to your actions, whether it's mouse clicks, keyboard presses, etc. Games are not the only event-driven interactive programs, but it's one of the most popular ones. So in this lab, the goal would be to finish an incomplete code base for a game. And the game is a version of Asteroids with a particular art theme that is heavily influenced by a painter called Mondrian, who used to create these geometrical pieces with primary colors. So that's the goal of this lab. And what I'll do in this video lecture, as with previous ones, is to go over some of the fundamental concepts you need to know about programming, and C programming in particular. And then I'll give you some hints about some of the tasks that need to be done. By the way, it looks like it's a lot of work, but actually this assignment, a lot of it has been done for you, and you're sort of putting in some of the key pieces, which itself is not a lot of code to write. So a lot of the code has been written for you, and I would encourage you to actually try and read all the rest of the code. You might not have to read all the code in order to do your tasks for this lab, so I do want to encourage you to read it just to get an idea of how to write something like this. So before we start with a more complicated example of event-driven programs, let's look at a very simple event-driven program where we have a while loop that loops forever. So 1 is true always, so it's going to continue this while loop, and it's taking one character input from the user, and then it does something from it, so something using that character. So let's assume that it's doing something very simple, just for the sake of argument. I'm going to use this simple program to motivate a aspect of C syntax, which is quite useful, especially when you're dealing with handling events. So usually when we have a character input, we could match using an if statement, whether it matches A, then it could printf apple and a new line, and then it would go and accept another character, and so on. So if it gets another character and it is a new line, then it does nothing. So let's say it just ignores new lines. So if you wanted to write a interactive event-driven loop where the user types in a character and it responds, then this is kind of the structure you would imagine if you have access to an if statement and then you use an else if statement. So if I wanted to compile this and run it, if I type in an A, types in apple, and I can type in A and apple. If I type in nothing, it does nothing. So that's not very exciting. But so I press Control C to come out of this loop. And so if I wanted to add, for example, another character, like else if C equals B, then print banana, then I have to add another else if statement. So now it can accept A and B, but it becomes very tedious, and so C provides a slightly simpler way in C syntax to deal with these sort of consecutive if, else if statements, and it's called a switch statement. Switch will take a variable in this case a character, and then you can match each of the any of the values that C could be can be written down as a case statement. So case A, for example, is something where we want to print apple, right? And then case B, we want to print banana. Now, one problem with this is that the case statement has a block. So in this case, this statement here will fall through to the next case automatically and execute the next statement as well. So so it'll check if it's B as well. So instead of doing that, we want to just break out of this block. Then we have to put an explicit break there. And so we need to put that explicit break here as well. And so now what it has done, so we also need the case for new line character. That's another constant. And it does nothing. And then does a break, right? It always does a break out of that particular case. So if I remove these, and now instead of using the if-else statement, I'm using this case statement. You can see that it accomplishes the same thing. So you type in A, it types in B as banana, I type in enter, doesn't do anything, and then I can control C out of it. So that's a way of using the switch statement to accomplish the same thing as a lot of if, else if statements. The other thing you can do is, since it falls through automatically without a break, I can also do something like this, where there is a case A and case capital A are handled using the same action, and the same thing with B. So when I type in a capital A or a little a, it'll produce apple and banana. So that works as you would expect. Right? So let's the only other thing that is of use in a case statement, in a switch statement, is that you can have a default, and a default just says if none of the other cases match, then it'll always match the default as the last resort. And so I can say nothing matched here, and it's kind of break out of that. So let's say I do A, B, C. It says nothing matched because I haven't put in a rule yet for C, and it just will keep doing that. Notice that it just does nothing when there's a new line. If I wanted to come out of this program sort of gracefully, I could put a case EOF, and then this would be a hard return statement. There's no need for a break because it's going to exit the function right after this break. So I'm going to CC switch complete, A dot out, and then I put an A, a B, a C says nothing matched, and then capital B, and then if I press control, keep the control key pressed and press D, it will exit the program. So in most real world systems, like windowing systems like Windows, or systems like Android or iOS, or any of these sort of large-scale systems that serve Windows and take user input in terms of mouse clicks or keyboard interaction. There's so many different types of events that you don't really want to handle all of them in your program often. you might only be interested in a small number of them. Like you might be interested in a mouse click or a key press or a key release, and you don't really care about any of the other events that you might that other programs might want to deal with. So typically in this kind of systems, you have a way of saying, oh, I'm interested in only these events and only show me these events, and then you can switch on those event types and then handle them. Another way to deal with this is to simultaneously say which events you're interested in. So you're interested in mouse click, and also telling the system using, so this is just an abstract function like some event handler. It says on a mouse click, here's a function to call. On a key press, here's a function to call. And these functions are defined by you as the programmer. So when there's a mouse click, you handle a mouse click. When there's a key press, you handle a key press. And when there's a key release, you handle a key release. Now, what are these functions? You can see these functions are being used as an argument to another function. So this function, handle mouse click, is being passed as a function to add event and handler. So how is this function being used as a parameter to another function? And the answer, as always in C, is we are passing a pointer to this function into this other function that receives a function pointer and then calls the function that's pointed to by that function pointer. So let's look at this new piece of C syntax and see how to define a function pointer and how to use it in a program. So let's look at an example of how to define a function pointer. So before we pass a function as an argument, let's just look at how we can print out the actual pointer value of any function. So I've defined this very simple function called printNum. It takes an integer and then it just prints out that integer using this printf statement. It says number is, and then it prints out the number. So very, very simple function. But in my main function here, what I've done is I've printed out using %p, which is the printf sort of type for pointer. And I'm just putting printNum here. So printNum is going to be the pointer where this code for this function printNum sits in memory. So everything is in memory. Everything has a pointer because it's in memory, and because pointers are simply addresses in memory. So what this is going to do is print out the location in memory where this function printNum is defined. So let's just run this code, and it's called callback.c, and I press a.out, and you can see that printNum is a function that sits in this memory address in my computer here. And so what we want to do next is use this function printNum as an argument to another function. And so here's a function that I've commented out. It says, so let's write the definition for this function. I think it'll help you understand the concept of a function pointer and how to pass it. So this function is called call my function n times, and it just takes a function. In this case, a function, as I said, is just a pointer. So it takes a function pointer, and then it takes a number, and then it calls that function that many number of times. So in this case, it's going to call printNum 6 times. And so let's call this function. It's a void function because it doesn't produce any output. It just calls printNum. And now we want to write a type declaration for a function pointer. And we know that the function we want is the same type as printNum. So it's going to return a void because printNum returns a void. And then it's a pointer to a function. So we have to say it that way. And it takes an integer as an argument. So this is how you define a function pointer in C. This f is a function pointer to something that takes an integer and returns a void. The syntax is a little ugly, but there's nothing to be done about that. And then the second argument, the first argument, as you can see, is a function called print. So the same type as print num. I don't have to call it print num because it's a variable, just like any other parameter. And this is an integer, so we just say int num as my second argument. And what I do next is I do for int I equals 0, I less than num, I plus plus. I'm going to call this function f that many number of times. So this is going to call it num times, right? So it's going to call it with 0, 1, 2, 3, all the way until num. And then, actually before I do that, let me just do one thing before I call it n times. So let me just print f, and I say pointer is, and then I print out the actual value I get as a function pointer. So I'm just printing out this parameter f, and I know that it's a function pointer, so I'm going to just print it out. So let's just see what it prints out. It should print out the same address as print num was printing out in the main function. So let's clear this, compile it, a.out. So notice that print num is printed in the main function. That's the pointer to that function print num, and then I call my function n times function, and in that I passed a function pointer. You can see that it's exactly the same as the other value that I printed out. So notice that this printf, which prints out the pointer to print num, is the same as this one, which is printing out f, which is this first argument of this function, call my function n times, which I'm passing a function pointer. So it's not surprising, but it's good to check that the print is printing out the right thing. It's printing out the same pointer. And now what I can do is for int I equals 0, I less than num, I plus plus. I'm going to call this function the number of times equal to this second parameter num here. So every time it calls it, it's going to call print num with a new value I. So you can try to guess what it will print when it runs this program. So it's going to call this function f, which is the first argument, print num. It's going to call it 6 times, and it's going to print what. So try to predict what it will do. So let me compile it. So hopefully this is what you expected. It prints it calls the print num function n times, so 6 times in this. So 0, 1, 2, 3, 4, and 5. So it calls print num 6 times, and each time it calls print num with the value of the number of times it's called it so far. So it called it 0 times, 1 time, and so on. So you can see in this code that it's calling the function repeatedly, and it's using this f here. And this is exactly the idea behind callback functions. So we say, take this function as an argument and call it when something happens. So maybe some event happens, or under some situation, it's very convenient to have the ability to call a function, basically pass a function as an argument to a function, another function. So this is a function that takes another function as an argument and then calls it. So that's one of the sort of ways to write code that can do different things based on different events happening in the program. So it's very, very useful when you're writing event-driven programs in particular. Here's another example of a function pointer. Here's a function that you've used many times before. It's a function that reports the length of a string. So this is returning the length of the string as a size underscore t typed variable. And this variable is called a in this program, and it gives the length of a string. In this case, we're going to use this constant string called hello world. Now we define a function pointer, and the function pointer is also returning the same thing as strlen is size underscore t. It's a function pointer, so we have to use this bracket syntax with a pointer here in front of the name of the variable. And then there's another bracketed part which tells you what the arguments of that function is that's pointed to by this function pointer. So it takes a constant char star, a string. And I'm assigning it using just a standard C assignment to strlen, which itself is a function pointer, so I can just use equal to make an assignment. And now we can show that when I do this printf, that strlen and the function pointer have the same pointer value. And I can compute, you can call that function just as if it was a standard function call. So the function pointer I can call on the same string, and I would expect this size to be the same. This value b should be the same as this value a, right? Because all I've done is called strlen using this indirect way of calling it through a function pointer. So the result of the call should be the same. So let me just compile this program. So function pointer a.out. So you can see that the strlen pointer is that, and the function pointer value is identical to it. And the length of hello world using either strlen directly or using the function pointer is both identical at 11 characters. Let's look at one more example of using a function pointer. And a function pointer is often useful when you want to sort arrays, and the arrays could be of different types. So for example, if you want to sort an array of ints, you might want to use the same function, qsort, which is provided by the C standard library, whether the array is an array of integers or an array of doubles, or in fact even an array of structs or function pointers. You want to sort them. You want a single sorting function like called qsort, and you want some way to evaluate which. So this is the first variable. The first parameter to qsort is this variable values here, which is an array which has a bunch of numbers, and you can see that they're not in sorted order. We need the size of that array, which is defined as num. We need the type of each element of the array. In this case, each element is of size of int, and that's just used to iterate over that memory. So you can always jump over to the next element of the array if you know the size of each element of the array. And finally, here's the function pointer. This is a pointer to a function called CMPFunc, and which is defined here, which is a function that returns an integer, and the integer it returns is 0 if the two values that it's comparing are equal. It's -1 if one value is, so first value is less than the second value, and it's +1 if the second value is greater than the first value is greater than the second value. So it's either -1, 0, or +1 depending on whether A is less than, equal to, or greater than B. So those are the first two. So notice that in order to capture that any type can be sorted, it's taking a void pointer as an argument. And so both of these are a pointer to each element in this array, and we don't know what type it is. So we're using a pointer in order to avoid declaring the type. And so the first thing we do is declare that A is an int pointer, and then we dereference it. It's the same way we say B is an int pointer, and then we dereference it. And then the integer value we want is simply produced by subtracting A from B, right? So what we're going to do in this main function is first print out the list in unsorted order. Then we're going to call qsort to sort values in place, and then print the result of sorting. So notice that this way of sorting the array requires you to pass a function as basically you're passing a function pointer to qsort in order to sort this. So if I compile this, you can see that before sorting the list was the original, and then after sorting the list. And we had to do a little bit more effort in order to make our code generic. Let me briefly talk about the setup for Lab 9. It's as straightforward as before. You grab the file from the URL, and then you can uncompress it. And when you go into the directory that it creates, you can add it to your repository and so on. But what you have to do in this lab 9, is to look at roids.c and search for the string task. So the first task you actually find in the file is task 3, which is not what you should do first. And the first task you should do is task 1, which is further down. And so first do task 1 by searching for it, and then you have to implement the callback function key down, which is what the program should do whenever the key gets pressed. And the description of the requirements are given in this comment over here, and the same thing is true for task 2, as you can see, which is right below task 1, which is what happens when you do key up. So task 1 and 2 are really easy. I'm not going to talk so much about that. What I'm going to talk about is task 3 actually, and talk a little bit about what you have to do in task 3. So task 3 is actually just an extension of the function which is to draw the ship. Okay, so we are doing a ship which is going to fly around and shoot asteroids, or mondroids in this case, and we have to draw the ship triangle, which is the x and y coordinate of the center of the ship, and we try to recover the top vertex of the ship. And the top vertex of the ship depends on the angle in which the ship is facing. The ship angle is defined as the value a inside the ship struct. And so what you should do is carefully look at this file and look at the ship data structure. But in this case, we are computing the 3 vertices of the ship, because it's just a triangle. So this dx and dy is the top vertex, lx and ly is the lower left vertex, rx and ry is the lower right vertex. And when we want to draw the ship, we have to just draw a triangle that connects these 3 points together, and we pass it the ship color. And if it is under power, so if you're pressing the key that is pushing the ship forward, it also draws a smaller triangle. It's just the flip side of the larger triangle. So it's just a small triangle at the bottom of the other triangle, sort of. It's a kind of mirror image, so you can see that it does a minus of the position. Task 3 is to draw the ship. So right now when you draw the ship, it does do the right thing and wraps around so as you go past the left corner, you'll see that it flips around and comes around the right corner, because the left edge and the right edge are joined together, and the top edge and the bottom edge is joined together. And we've seen this before in previous labs. So you can see that the surface of this area that we see as a flat two-dimensional shape is in fact internally looks like a torus, right? So the top and the bottom are merged, and the left and the right are merged together. So it looks like a donut internally. So mathematically it's a donut, but when you see it, it looks like a flat two-dimensional image. Task 3 is to make sure that the wrapping happens correctly. And let me just show you what that means with an example to put you on the right track for solving task 3. So task 3, 4, and 5 in this lab have the same basic idea. You have to make sure that the ship in this space is wrapping around correctly. So what I've done is I've put the ship in this corner area here to explicitly show you what that means. So as you can see here, if you look at these numbers below, I've added a printf statement that prints out the sort of the center x value, the center y value, the left x value, the left y value, the right x value, right y value of the 3 coordinates of the triangle. But in order to draw this triangle correctly when it's wrapped around, so let me just swivel this around without moving it. So you can see what's happening here. The edge of the triangle is over here, and then I can move the edge of the triangle around. So now it's up here to the upper left corner, and it's turning, and now it's in the upper right corner, and now it's in the lower left corner. So you can see that in order to draw the triangle that's the ship in the right way when it's wrapped around, you essentially have to draw 4 triangles. There's one triangle sort of up in the upper left corner, one triangle on the upper right corner, one triangle in the lower left, and one triangle on the lower right. So in order to get the triangle vertices all drawn correctly, you need to be able to not just draw one triangle for the ship, but actually 4 different ones. And the same goes for the thrust triangle that's going to come at the bottom of the ship when you're under power. So it's not so easy to control the thrust to get it into the corner like I've done here. So in fact what I've done is I simply put in the initial coordinate not to be the center of the canvas but in this corner. So if you can get your ships to correctly render all these 4 triangles, then you've done the job for task 3, 4, and 5. They're all very similar. Okay, so good luck.